First of all, welcome to everyone to the this is special lecture for the KIAS 25th anniversary. First of all, I would like to introduce KIAS President Jae-kyung Choi.
This year is the 25th anniversary for KIAS. So to celebrate this important anniversary, we have been organizing a series of Quadranscentennial KIAS lectures. Today, we are very honored to have Professor Henri Darmon as our speaker. I hope we'll be able to learn a deep theory on complex multiplication from Henri Darmon's lecture. Thank you.
Okay, today's speaker is Professor Henri Darmon. I'd like to introduce him briefly. He received the PhD degree at Harvard University in 1991. He joined the faculty of McGill University in 1994. Now he is a distinguished James McGill Professor. He was also awarded a Cole Prize of the AMS in 2017. Please give a warm welcome to the today's speaker, Professor Henri Darmon. Please start.
Thank you very much for your kind introduction. So it's a great pleasure to be giving this Quadranscentennial lecture at KIAS. In fact, I was very pleased to learn this lovely new word. I hadn't heard this before, Quadranscentennial lecture. So the theme of my lecture will be the theory of complex multiplication and some possible generalizations. So going a little bit beyond the setting of CM fields. And I want to begin my lecture by giving you a sense of the scope of the classical subject and its various applications by talking about one of the basic objects of the theory, one of the most standard classical modular functions, the J function. So this function is characterized as the unique holomorphic function on the Poincare upper half plane, consisting of complex numbers with strictly positive imaginary part, which is holomorphic and has these two basic symmetries. It's invariant under translation and under inversion, and therefore under all Mobius transformations by matrices in SL2Z. And furthermore, one requires that it have a kind of expansion at infinity, so to speak. If you replace Z by e to the 2 pi I z, then in terms of that parameter, it has a power series, Laurent series expansion with leading term 1 over q. And so this function arises in quite a few settings in mathematics. One interesting example, which is quite surprising when you first see it, is the celebrated identity that was first observed by John Mackay, that 196,884, which is the coefficient of q in this J function, is actually 1 plus 196,883. And the reason that's a remarkable observation is that this 196,883 occurs in ostensibly completely different guise in mathematics as a dimension of the smallest non-trivial representation of the monster sporadic simple group. So it appears in the representation theory of these finite simple groups. Another source of mathematical richness of the J function is that its values at certain distinguished arguments, the quadratic imaginary ones, there are CM points in the upper half plane, are interesting algebraic numbers. And the theory of complex multiplication actually asserts that these values are algebraic and defined over quite structured fields and have a lot of interesting structures, which I'm going to talk about now. And so an example of this, so here are a few sort of simple instances of the values of J at imaginary quadratic arguments. So J of I is 1728. J of 1 plus root minus 3 over 2 is 0, etc. So here are 3 examples where the J function actually takes integer values at these arguments. A slightly more complicated example is if you take the value of J at 1 plus root minus 23 over 2, then you get a real number which satisfies a cubic polynomial with these integer coefficients. It's actually an algebraic integer of degree 3. And the fact that this is a cubic irrationality reflects the fact that the quadratic field generated by the square root of minus 23 is actually of class number 3. And this number W actually generates what's called the Hilbert class field of this quadratic extension. So I'll be saying that a little bit more systematically in the coming few slides. So this theory of complex multiplication, the fact that these values of the J function and of other modular functions have nice algebraic properties, has many applications in number theory, including some quite modern ones, even though this was, so the basic theory was developed pretty much in the 19th century. It attained a certain maturity already in that century. But some of the applications that have been found of the theory are quite modern. So, of course, the most basic, the first application is the notion of explicit class field theory for imaginary quadratic fields, that one can actually generate essentially all the abelian extensions from values of the J function. But then there are also applications to the so-called ABC conjecture, which is a very basic fundamental Diophantine question. Starr's conjecture and the Birch-Swinnerton-Dyer conjecture. And these are all, of course, very much late 20th century topics. So I'm going to begin in this lecture by describing some of these connections, some of these applications of the theory of complex multiplication. By the way, don't hesitate if you have any questions during the lecture, don't hesitate to just, I guess, turn off your mute button and ask the question. Okay, so I'm going to begin by saying a few words about explicit class field theory. So if K is any quadratic imaginary field generated by the square root of minus D, say, then there's this lovely theorem of Kronecker, which asserts that the singular modulus J of tau, for tau in H intersected with this imaginary quadratic field, is an algebraic integer in an abelian extension of this K. And the set of all these values, as tau ranges over K, generates, together with the roots of unity, essentially all abelian extensions of K. And there's a way of saying that more precisely. In fact, the field generated by all these values is contained in the maximal abelian extension of K. And that maximal abelian extension is an extension of exponent 2 of that extension. So up to an exponent of 2, you get all the abelian extensions. And the field of definition of the singular modulus, J of tau, is what's called the ring class field attached to tau, and I'll simply denote it by H tau, H sub tau in my lecture. Okay, so some kind of abelian extension whose degree, of course, depends on the discriminant of the quadratic equation, which is satisfied by tau. Okay, so among their striking properties that these singular moduli enjoy is the fact that they have rather interesting factorizations. So if tau1 and tau2 are two imaginary quadratic numbers of discriminants d1 and d2, and h1 and h2 are the associated ring class fields, then we can consider the quantity j of tau1 minus j of tau2, the difference of the two singular moduli, which of course belongs to the compositum of these two ring class fields. And it turns out that these numbers, not only are they algebraic, but they are smooth in some sense, that they have factorizations which involve relatively small primes of relatively small norm. And I'm going to illustrate, so I'll state the theorem that the theorem which was proved by Gros-Zagier in the mid-1980s, so surprisingly late actually in the historical development of the subject, asserts that the norm of J infinity tau1 tau2 is divisible only by primes which are less than the product of the two discriminants. And in fact, even more, that divide a quantity like d1, d2 minus a square over 4, where x squared is less than d1, d2. And not only that, but these primes, so there's a sort of basic limitation on the size of the primes and also on their congruence properties. So these primes have to be either inert or ramified in both of the quadratic fields, K1 and K2. So that was a theorem that was proved by Gros and Zagier. Now, The connection with the ABC conjecture, and the fact that these numbers are have such striking factorizations, can be seen by considering the following example. So if I take, for example, j of I and j of 1 plus root minus 163 over 2, and that the reason I chose that quadratic number in the example is this actually is the largest discriminant, minus 163, of an imaginary quadratic field of class number 1. And so these values are actually both integers for that reason. And we saw what they are. So the difference of j of I and j of this turns out to be this number with this rather nice, simple factorization. And you can see that all the primes that appear here are less than 4 times 163 over 4. The product of the two discriminants divided by 4. And well, if you write down j of I minus j of 1 plus root minus 163 over 2, you get this sum of two numbers, which are also very smooth and the product of small primes with fairly large multiplicities. You have a 3s and 18s, etc., in the exponents. Now, this kind of sum of two powerful numbers being another powerful number is an apparent contradiction to the ABC conjecture. And indeed, it would contradict the ABC conjecture if these kind of examples occurred infinitely often. And the reason why they don't has to do with the fact that there are only finitely many quadratic imaginary fields of class number 1. Now, you can actually simplify this expression here a little bit because there's a common factor of 2 to the 6 and 3 cubed in all three integers. And when you divide by that, you get this rather remarkable instance of two very smooth numbers, very powerful numbers, which are consecutive. Okay, and so indeed these look like counterexamples. And Granville and Stark in the maybe 90s or so, or late 80s, I think, exploited this connection to show that if a strong form of the ABC conjecture, some ABC conjecture over number fields is true, then that would imply that there are no Siegel zeros, that Dirichlet L functions attached to odd characters have no Siegel zeros. And the reason is that an L function with a Siegel zero leads to a quadratic imaginary field whose class number is small relative to its discriminants, essentially. Oh, okay. Now, so another connection which sort of ties in with the Stark conjecture is the fact that there are other modular functions which are actually units in the field of modular functions or in the ring of modular functions on the open modular curve. So for example, this famous infinite product, q times product of 1 minus q to the n to the 24, the so-called delta function, is a remarkable instance of a modular form of weight 12, which is everywhere non-vanishing on the upper half plane because it has an infinite product expansion which converges everywhere. And so it has no zeros or poles on the upper half plane. All its zeros and poles are concentrated at the cusps. And it's invariant under all of SL2Z, under all Mobius transformations. And so the basic fact then is that if you take any integer n greater than 1, then you can consider this ratio, delta of z over delta of nz. That is actually a form of weight 0. So it's a genuine function. Invariant under a slightly smaller group than SL2Z. It's invariant under the so-called Hecke congruence group, gamma naught of n. And it's an example of a basic instance of what's called a modular unit. So it's a holomorphic function, and it's invertible on the entire upper half plane. And the values of this modular function at CM points inherit the same properties. Not only are these values algebraic integers, as was the case for the values of the J function, they're actually algebraic units. They give units in abelian extensions of quadratic imaginary fields. And these units are called elliptic units, and they have many applications. They play a fundamental role, for example, in the work of Coates and Weils on the arithmetic of CM elliptic curves. And so one of the connections of Stark's conjecture is that these units appear in leading terms of L functions. So if chi is any character of the Galois group of one of these ring class fields, then we can consider the art in L function attached to chi, which is given by this Euler product. And the Kronecker limit formula expresses the first derivative of this art in L function at s equals 0 as a linear combination of logarithms of these elliptic units. And so this tells you that the leading terms of these art in L functions are given as logarithms of units in these abelian extensions. And that was what's sort of, that forms the basic prototype for this fairly daring at the time conjecture of Stark, which is that which predicts in some sense that leading terms of L functions, more general art in L functions, are also logarithms of special units, the so-called Stark units. And in that generality, the statement is still widely open, I mean, very much open and very conjectural. But it was certainly motivated by this basic result of Kronecker. And finally, maybe the most recent application of CM theory, major application, I guess, arises from this fantastic theorem of Weils from the mid-1990s, which says that every elliptic curve over the rationals is uniformized by modular functions. So if E is an elliptic curve given by some equation like this, where A and B are rational parameters of the equation, so by such an elliptic curve one can associate with an arithmetic quantity called the conductor, which is an integer, which I'll call n. And then the statement of Weils' theorem is that there are rational functions, x, y, in j of tau and j of n tau. So x of tau can be expressed as some rational ratio of polynomials in these two functions, j of tau and j of n tau, likewise y of tau, such that these two functions satisfy the equation of the elliptic curve. And what that tells you is that now if you vary, if you look at x of tau, y of tau, as tau ranges over these quadratic irrationalities in the upper half plane, you get a systematic supply of algebraic solutions to the elliptic curve equation. So you get algebraic points on the elliptic curve defined over Q bar. And these are called Heegner points. And the subgroup of E of Q bar generated by these points is quite large. So one can show that it's always of infinite rank. So it's a very interesting structure to study in its own right in connection, for example, with Iwasawa theory. And there's been a lot of work done in the last decades trying to understand the deeper aspects of these connections. Now, the Birchman-Swinnerton-Dyer conjecture asserts that the Haseve-L function of the elliptic curve carries information about its arithmetic. And so, notably, the order of vanishing, so Weils' theorem implies that this L function has an analytic continuation to the entire complex plane, and the BSD conjecture asserts that the order of vanishing at s equals 1 of this L function is the rank of the Mordell-Weil group of the elliptic curve. And one of the major difficulties in sort of understanding this conjecture is sort of the challenge of being able to produce in a systematic conceptual way rational or algebraic points on the elliptic curves in question, especially in situations of higher rank. And indeed, aside from Heegner points and sort of more or less fairly direct variants of this method, there really are no other methods known, at least unconditionally, to produce such interesting points. Okay, so now I'll say a few words about what evidence we have for the BSD conjecture, thanks to these Heegner points arising from the theory of complex multiplication. So the first is this fantastic theorem of Gros-Zagier, which says that the group of Heegner points in E of Q, so the contribution of these Heegner points to the set of rational points on the elliptic curve, is always of rank at most 1, which is a little bit of a bad news in a way. It means that we don't really understand the arithmetic of higher rank curves via this theory of complex multiplication. But on the other hand, there's a direct connection with the behaviors of the L functions, which is very nice. and very important for the BST conjecture. And so this Heegner's group, this group of Heegner points in E of Q, is non-trivial precisely when the L function has a simple zero at the center, at s equals 1, the center of symmetry for the functional equation. And then there's a complementary result, which is more on the arithmetic side. So this theorem is really concerned with the Hasebe-L function. On the arithmetic side, there's this theorem of Kolyvagin, which says that if the order of vanishing of the L function is at most 1, and therefore the Heegner point is non-trivial, or then this order of vanishing of the Hasebe-L function is equal to the rank of the Mordell-Weil group, as was predicted by the Birchensprint-Dyer conjecture. So this gives a proof essentially of a weak form of the BST conjecture in analytic rank 0 and 1. And this kind of circle of ideas was exploited as a beautiful, more recent result by Bhargava, Skinner, and Wei Zhang, which uses these two results to show that the Birchensprint-Dyer conjecture is true for a positive proportion, fairly large, or at least 66%, of elliptic curves, all of them having rank 0 and 1. And so the main thing I wanted to say about this is that none of these results would have been possible without Heegner points that arise from the theory of complex multiplication. It's really because of that structure that we have this kind of handle on the arithmetic of elliptic curves in the setting of curves of rank 0 and especially of rank 1. Okay. Now, in light of all these applications to arithmetic, it would be nice to be able to go beyond the setting of quadratic imaginary fields and have an analogous theory in other settings. And so that problem of generalizing the CM theory to other base fields is known as the Kronecker-Jugendtraum, dream of youth, or Hilbert's 12th problem. So it was first, I guess, posed by Kronecker and also raised by Hilbert in one of his famous list of open problems that he presented at the Congress in Paris, the ICM in Paris. And here I was supposed to have two pictures. I don't know what happened to my slides here. There seems to have been a problem, but anyway, sorry about that. Okay, so I'm going to just read you the statements that Hilbert made of this question in 1900. So finally, the extension of Kronecker's theorem to the case that in the place of the realm of rational numbers or of imaginary quadratic fields, any algebraic field, whatever is laid down as the realm of rationality, seems to me of the greatest importance. I regard this problem as one of the most profound and far-reaching in the theory of numbers and of functions. And so put simply, the question then, and it's going to be the theme, I guess, of today's lecture, is to try to describe a conjectural extension of the theory of complex multiplication, which applies in particular to the setting of real quadratic fields, which could be viewed as the first instance where Hilbert's 12th problem remains open. And the first difficulty in this question is that, well, if we think about the theory of complex multiplication as a model, we would like to obtain abelian extensions by evaluating something like a modular function at distinguished arguments in some kind of symmetric domain, like the upper half plane. But the complex upper half plane does not have any real quadratic irrationalities, right? We've removed the real line, which is the boundary of the upper half plane. And so the real quadratic numbers lie on the boundary. And so we can't evaluate, modular functions have essential singularities at that boundary, and we can't, in a simple-minded way, evaluate these functions. So this leads us to try to propose using p-adic methods as a possible approach. And the reason is that on a very naive level, the p-adic upper half plane, which is simply the complement of the projective line over QP inside the projective line over CP. So it's really just an analog of the upper half plane where you replace the reals by the p-adic. So you work with a different completion, essentially. It does not suffer from this drawback. So indeed, if we have like a real quadratic field and P is a prime, which is inert or ramified in this field, then the p-adic upper half plane for that P contains plenty of elements in K. And so we say that a point in the p-adic upper half plane is a real multiplication point or Rm point if it belongs to this intersection. And the hope is that ring class fields of real quadratic fields can be generated by these values at Rm points of suitable functions on the p-adic upper half plane. And then the question, of course, becomes, what are these suitable functions? So these are the kind of objects that Hilbert was asking for in his statement of this problem, functions that would play the role of modular functions in this setting. And in the classical setting, we simply looked at functions on holomorphic functions or meromorphic functions on the upper half plane that were invariant under the modular group, under SL2Z. In the p-adic setting, one could also consider something like holomorphic functions on HP. Now, in the p-adic world, there's a nice notion, a very usable notion, which plays the role of holomorphic functions, which is the so-called theory of rigid analytic functions. And I won't go into the details here of the technical definition, but roughly speaking, a rigid analytic function is a function which on suitable nice subdomains, the p-adic upper half plane, so-called affinoids, can be uniformly approximated by rational functions. And this notion was introduced historically by Tate. And the most important property that these rigid analytic functions have is the principle of analytic continuation. That's absolutely fundamental for us, namely two rigid analytic functions which agree on some small disk agree everywhere. And so one has a kind of a principle of patching, as one does with holomorphic functions. Okay, and then we have, of course, once we've defined the notion of rigid analytic function, we have the notion of rigid meromorphic function simply being a ratio of rigid analytic functions. And it would be natural to consider rigid meromorphic functions on the p-adic upper half plane with nice transformation properties under the modular group SL2Z. Okay, so that leads us to the second difficulty, however, which is that the modular group SL2Z does not act in a nice way on the p-adic upper half plane. This action is not discrete for the p-adic topology. And more precisely, the group of translations, z goes to z plus n with n in z, and an integer, already has non-discrete orbits. And the reason is that although the integers are discrete in the real line, in the p-adic numbers, the integers are very much non-discrete. They have plenty of accumulation points. And so we can take the, I'll denote by script m, the space of rigid meromorphic functions on HP, endowed with this translation action of SL2Z. And so this is defined in the usual way by just translating by Mobius transformations for a function. And one way of restating the problem is to simply observe that there are no non-constant elements of this space of meromorphic functions which are invariant under SL2Z because the orbits are just too big. And in other words, the H0 of SL2Z with values in M is CP. Okay, so this leads us to the notion of rigid meromorphic cocycles, which is really the basic object that I want to discuss in the entire lecture series, in fact. So the first thing we do is we work with a slightly larger group than SL2Z. Namely, we work with the group where we invert P, the so-called Ihara modular group, SL2Z of 1 over P. Now, this may seem like a funny thing to do because by enlarging the group, of course, you're only making its action even less discrete than it was before. And we're going to, the theorem I'm going to describe is very much a multiplicative theory. So instead of working with M, we work with the multiplicative group of non-zero elements of the non-zero meromorphic functions under multiplication. And now the fact I observed on my previous slide that there are no interesting gamma invariant functions implies that the H0 of gamma with values in M star is just CP star, the constant functions. And if this module has a uninteresting H0, one thing one can try to do is work with its higher cohomology. And that's one way of motivating the definition that I'm about to propose. We say that a rigid meromorphic cocycle is a class in the first cohomology of gamma with values in M star. And we say that such a class is parabolic if its restriction to all the parabolic subgroups of the Hara group gamma are trivial. And an elementary observation, which is absolutely fundamental for the application of this notion to explicit class field theory, is that one can meaningfully evaluate rigid meromorphic cocycles at Rm points. And the way that's done is very simple. So we simply observe that an element, to say that the tau in the p-adic upper half plane is an Rm point, is equivalent to the statement that the stabilizer of tau in gamma, in the Hara group, is a group of rank 1, generated by a matrix, which I'll call gamma tau, the so-called automorph of tau. Now, for most tau in the upper half plane, the stabilizer is trivial or at least finite, but for these Rm points, the stabilizer is infinite and rank 1. And so if we have a rigid meromorphic cocycle, capital phi, and an Rm point tau, then we can define the value of phi at tau, which I'm going to denote in this way, phi of square bracket tau, by simply evaluating the cocycle at the automorph. So phi of gamma tau is going to give me some kind of meromorphic function on the p-adic upper half plane. And I then take this meromorphic function and I evaluate it at the fixed point of gamma tau, namely tau. And this gives me a numerical invariance. And that's what I call the value of phi at tau. And this quantity is a well-defined invariance. It's independent of the cocycle. It depends only on the cohomology class of phi in the first cohomology of gamma with values in M star. And moreover, this value satisfies this nice invariance property that it depends only on the gamma orbits of tau, this value. So this doesn't contradict the fact that gamma acts with non-discrete, very large non-discrete orbits, because of the fact that this the value is only defined on the Rm points. So this phi of tau has no nice continuity or analyticity properties. So it has to it really depends not just on the actual tau in HP, but also on this automorph. Okay, so that's the notion of this value. And then the basic conjecture that I formulated some 4 or 5 years ago with Jan Vonk is that if phi is any rigid meromorphic cocycle, then the value of this phi at tau is an algebraic number. And moreover, it belongs to a composita of ring class fields of real quadratic fields. So there's a certain field associated to phi, to the cocycle itself, which is called the field of definition of phi, and the H tau, the usual ring class field associated with tau. And phi of tau should belong to the compositum of those two fields. And so what I'll do in the rest of this lecture is I'll explain how to make this conjecture a little bit more explicit, and I'll try to convince you that these numerical values satisfy very much the same phenomenology as the singular moduli that we're studying in the work of Gross and Zagier, for example. And so I'm going to first make the conjecture more concrete and explicit by giving a classification of all the rigid meromorphic cocycles. And then I'll also describe some of the numerical evidence that's been gathered in support of this conjecture. So to begin with, as a prelude to understanding these multiplicative cocycles, one needs to understand something about the additive theory. So one can consider the module, which I'll call M sub k, of rigid meromorphic functions on the p-adic upper half plane. But now I take the additive structure. So I look at the additive group of meromorphic functions endowed with the following weight k action. So I slash f by gamma, by substituting here, but then multiplying by the usual automorphy factor for modular forms of weight k. And there's a logarithmic derivative map which sends m star with the weight 0 action to m2. So additive, multiplicative to additive, sending f to df over f. And since this logarithmic derivative is an equivariant for the action of the group, it induces a map also on the first cohomology. So it maps rigid meromorphic cocycles to classes in the H1 of gamma with values in M2. And the strategy then to understand these multiplicative cocycles is to begin by classifying the first cohomology of gamma with values in M2. And so this actually, the ideas that go into this classification go back to the work of Marvin Knopp in the late 70s and probably even earlier than that in some sense. And so that, I mean, or at least some closely related question of classification had been considered by Knopp and later by some of his students, as I'll mention later. So what Knopp considered were not the rigid meromorphic cocycles, but rather an algebraic, purely algebraic analog, which simply consists of cocycles with values in rational functions. So I'm going to call MK dagger the space of rational functions on the projective line. Now, the space of rigid analytic or meromorphic functions is in some sense a completion, because as I said before, the rigid analytic or meromorphic functions are uniform limits of rational functions on these nice subdomains, the aphanoids. And so what Marvin Knopp did is he classified the classes in the first cohomology of SL2Z with values in the rational functions for this weight k action. So he called this a rational modular cocycle of weight k, and this is simply a class in this first cohomology. And if phi is a parabolic rational modular cocycle of weight k, then he also defined a notion of what he called a rational period function of weight k. That was simply the value of this cocycle on the matrix S. So S is the standard element of order 2 in SL2Z, the matrix 0, 1, minus 1, 0. Okay, I forgot to write it in the slide, but that's what it is. Okay, so this is a rational. So it turns out that this rational period function satisfies a number of somewhat complicated functional relations. So it satisfies this relation, relating its values at z and at minus 1 over z. It satisfies an even more complicated three-term relation, relating its values at z, minus 1 over z minus 1, and z minus 1 over z. Okay. And what Knopp did, quite remarkably, is at least took the first steps in the full classification of this space of functions. Okay. Now, it turns out that the rational period functions are intimately connected to binary quadratic forms of positive discriminant, and therefore to the arithmetic of real quadratic fields, which is quite a striking fact. So if f is any binary quadratic form with non-square discriminant, then we say it's simple. If it's a value, if its roots, which I call WF plus and WF minus, are of opposite signs. So one of them is negative and the other is positive. So in other words, the geodesic joining those two roots has to cross the y-axis on the upper half plane. And if C is any SL2Z equivalence class of binary quadratic forms of some fixed discriminant, then we observe that the subset, so the C of course is an infinite set, it's an orbit under SL2Z of binary quadratic forms, but the set of simple forms turns out to be finite. And therefore, and then what Knopp did in 78, and then later this result was refined and strengthened by a number of people, notably Avner Ash, Youngju Choi, and Don Zagier in 1993, wrote a really lovely article where they gave a full classification by quite clever techniques of the full space of these rational period functions. And what they, one of the statements they prove is that if you consider the following expression, so you take the sum over all the simple binary quadratic forms in a given SL2Z orbit, and then you take simply the function which has a simple pole at one of the roots, and then you weight this by the sign of f. And the sign of f is, I guess maybe I should have said the sign of, yeah, what do I mean here? I should have said here the sign of WF. So you put a residue there, which depends on whether WF is positive or negative. And this turns out, this is a finite sum of simple rational functions, and it's actually a rational period function of weight 2. And moreover, any rational period function of weight 2 is essentially a finite linear combination of these basic examples. So that's the theorem that was proved by these people. And that was very much an inspiration for Vonk and myself when we turned to the question of understanding these rigid meromorphic period functions. So these results can be transposed to our setting. Namely, we can now, given any rigid meromorphic period function, we can look at its value at S, and that defines a function that we call a rigid meromorphic period function. And we can likewise classify them. And again, so they satisfy these functional relations, the 2- and 3-term relations, and a number of more complicated relations as well, which I'm not going to list completely. One of them, though, which is nice and simple, is the fact that it's invariant under multiplication by p squared, this function. And that, of course, precludes it being anything as simple as a rational function because of this translation invariance. Okay, so rigid meromorphic period functions are also connected to binary quadratic forms, but this time we have to consider SL2Z of 1 over P equivalence classes, so orbits under this larger Ihara group of binary quadratic forms, but this time with coefficients, of course, in Z of 1 over P. So we have to work over this larger ring where we've inverted the prime P. And the subset now of simple forms is now infinite, because you're taking orbits under this much larger group. But however, they have a nice discreteness property for the p-adic topology. Namely, if we consider exactly the same kind of sum, the sum of the sine of WF over Z minus WF, as F ranges over all the simple forms in an orbit under the Ihara group, this infinite sum converges to a rigid meromorphic period function of weight 2. And moreover, all other rigid meromorphic period functions are essentially finite linear combinations of these basic ones. So we have a classification which is quite similar to what you see in this purely algebraic result of Knapp, Choiseguier, etc. Okay, so having classified the functions of weight 2, we can then try to simply take the inverse under the logarithmic derivative map to get multiplicative invariance. And so if you do that formally, you're led to replace these infinite sums by infinite products of this form with exponents which depend on the residue, right? Which is again the sign of this form f. And so this rigid meromorphic function has a multiplicative analog. And so it lifts this under the logarithmic derivative map. And I'm going to denote by phi sub c star the class. It turns out that it defines a cohomology class with values not in M star, but only in M star modulo scalars. And this is what we call the rigid meromorphic cocycle modulo multiplicative constants attached to some analytic cocycle of weight 2. And so the zeros and poles of this object are concentrated on gamma translates of roots of simple binary quadratic forms in a finite collection of gamma orbits. So now that we've produced classes in here, the H1 of gamma as an M star mod CP star, we'd naturally like to understand which are the ones that lift to a class in the H1 of gamma with as an M star, to a genuine rigid meromorphic cocycle. But we have this fundamental exact sequence coming from the cohomology, taking the cohomology of the short exact sequence, the obvious one. And because the Ihara group is an amalgamated product of two copies of SL2Z glued along a common gamma naught of P, so to speak. So there's this very nice description of SL2Z of 1 over P due to the work of Ihara originally. Then one can actually show, one can analyze these cohomology groups and show that the two groups on the left and right are quite small and well understood. Namely, this ambiguity group, by which when you perform the lift, is a finite group. So it's very small. And the obstruction group, the second cohomology of gamma without CP star, is isomorphic to the first cohomology of gamma naught of P with values in CP star. So this one is at least of, well, I guess a finite co-rank. I mean, it's isomorphic to a finite number of copies of CP star. And so as a corollary, we find that the H1 of gamma M star is of infinite rank, because this H1 gamma M star mod CP star is huge. To every gamma orbit of binary quadratic forms of positive discriminant, we can associate such a cocycle mod scalars. And so it's of infinite Z rank. And the target here is of finite rank. And so there are many ways of producing elements in the kernel, and these then lift in an essentially unique way to a genuine rigid meromorphic cocycle. And so we find that this group is quite large, which is good. It means that the theory is not vacuous. And a particularly nice situation is when this obstruction group vanishes. And that happens precisely when this H1 of gamma naught of P is trivial, which happens when there are no cusp forms. Or as almost trivial, generated by the Eisenstein series. So when there are no cusp forms, it's a particularly simple case of the construction. So if P is in this set of primes, i.e. the modular curve x1 of P is genus 0, then this second cohomology is one-dimensional, so as small as it can be, and it's Eisenstein. So we understand exactly how the Hecke operators act on it, and they act via this Eisenstein Hecke eigenvalues. And in that case, we can show that this cocycle phi C bar star lifts uniquely to a class up to powers of a fundamental unit of the corresponding imaginary real quadratic field. So then we can systematically produce things which are almost as good as rigid meromorphic cocycles, the ones which are invariant up to a power of a fundamental unit. And indeed, if you are interested in questions of algebraicity and factorization, then the ambiguity of epsilon to the z is quite innocent. It doesn't affect either algebraicity or factorization properties. And so, let me see. So, yeah. So, okay. So now I'll say a few words about how we can use these objects then to describe a notion of singular moduli. So if tau1 and tau2 are two Rm points in the chaotic upper half plane, we can call phi tau1 and phi tau2 star the associated rigid meromorphic cocycles. Here I'm assuming that P is one of these small primes, so there's no issue about lifting these cocycles. And so they're attached to the class of these binary quadratic forms, having tau1 and tau2 as root. Then there's a kind of vague reciprocity formula, which asserts that the value phi tau1 star at tau2 is equal to the value of phi tau2 star at tau1 up to the ambiguity of the associated fundamental units. And so we then define this quantity, which is this value or that value, depending on, we call that the p-adic intersection number of tau1 and tau2. And this, it turns out, is going to play exactly the same role, what I'm going to say now, as the J infinity tau1, tau2 in the theory of compass multiplication. And so the main conjecture that I formulated with Jan in a somewhat more precise form is that this p-adic intersection number belongs to the compositum of the two ring class fields attached to tau1 and tau2, and it behaves in all practical important respects exactly like the classical difference of singular moduli in the work of Gross and Zagier. And so I'm going to illustrate this with an example. So if I take tau 1 to be the golden ratio and tau 2 to be 2 square root of 2, and then I let H1 and H2 be the associated ring class fields. It turns out in this case, because Q square root 5 has narrow class number 1, H1 is equal to the real quadratic field itself. And for 2 root 2, it's a little bit more interesting. The class field is generated by I over Q square root of 2. And then it turns out that, well, these 2 points, tau 1 and tau 2, belong to both the 3-adic and the 13-adic upper half plane. So I can do this calculation both 3-adically and 13-adically. And what happens when I do this, I get these nice values, at least here up to 200 3-adic digits of precision, and here up to 100 digits of 13-adic precision. So what you observe here is that the values actually depend very much on the primes, but they appear to be nice algebraic numbers. And indeed, so first thing, it appears that this value, this intersection number, is in the compositum of H1 and H2, and moreover on the part which is fixed by the product of complex conjugation and Frobenius at P. And if you study the primes that divide the product of two discriminants minus a square over 4, that was the quantity that appeared in the theorem of Gros-Zagier, if you remember, then these and that are non-split in both of the quadratic fields Q squared 5 and Q squared 5, you find that these primes are 2, 3, 5, and 13. Those are exactly the primes that satisfy these properties. And the norm of the numerator of our difference of real quadratic singular moduli is this integer, which factors as 5 to the 8 times 13 to the 8. And for the 13-adic invariant, the norm is this, which is 3 to the 8. So you see that you get only these small primes occurring in the factorization. And we also observe an interesting pattern, which is that the 13-adic valuation of the 3-adic invariant is the same as the 3-adic valuation of the 13-adic invariant. Namely, both quantities are equal to 8. That's not a coincidence. It turns out that it repeats in other experiments. And so here, for example, is a table of values of the intersections of square root of 2 and tau, as tau takes on these values, so some multiples of square root of 2. So for p equals 3, 5, and 13, we get these values here, at least numerically. Everything here is experimental and numeric. For 4 root 2, we get these values here. And so you notice here that 5 squared appears in the denominator of the 3-adic invariant, and 3 squared likewise appears in the denominator of the 5-adic invariant. Something similar happens here with one thing you observe here is that the values that you get are defined over this ring class field attached to the 7 root 2, which is actually turns out to be the narrow ring class field of conductor 7 for this real quadratic field, which involves the square root of minus 7. Now here for the 8 root 2, you get this value here, which the 3-adic value has both a 5 and a 13 in the denominator, both with a multiplicity of 2. And sure enough, you see a 3 appearing with multiplicity 2 in both the 5-adic and 13-adic invariants. And here in this other example, you find a 13 appearing with multiplicity 2 in the 3-adic invariant, with multiplicity 4 in the 5-adic invariant. And the mirror pattern is that in the let's see, my slide is frozen somehow. Yeah, there. In the 13-adic invariant, you see a 3 squared and a 5 to the 4. And then, okay, so something similar happens again with, okay, I'll skip over this a bit quickly. I'm getting a bit short on time. Okay. Anyway, you have a similar pattern in the last one. Okay. Okay, so one way of phrasing the conjecture about the arithmetic multiplicities of prime factorizations and these differences is that one can associate certain geodesic cycles on certain compact Riemann surfaces which arise from certain quaternion algebras, which are ramified at the prime P and the prime Q, where we're interested in understanding the Q-adic valuations of the P-adic invariants. And we can consider the topological intersection numbers of these two geodesics attached to the real quadratic embeddings attached to tau 1 and tau 2. Okay, so we call this the topological intersection number. And then the Gross-Zagier style factorization conjecture, which I formulated with Jan some years ago, is that these, for all Rm points, tau 1 and tau 2 of discriminants D1 and D2, this quantity is divisible only by primes, which in H1, H2, which lie above rational primes Q, for which first Q divides D1, D2 minus the square over 4, and the prime has to be both inert or ramified in both of the quadratic fields. And then finally, the quantity, the Q-adic valuation of the P-adic intersection number is equal to this intersection IPQ of tau 1, tau 2. And that explains this pattern, right? Because this quantity here is symmetrical under exchanging P and Q. Okay. Yeah. Okay, so finally, in conclusion, I just want to mention that these Rm values of rigid meromorphic cocycles lead to conjectural analogs of singular moduli, which share many of the same properties. And this has applications to class field theory, for real quadratic fields, Gross-Zagier style factorization formula. And what I want to do in the next lecture is explain, so what I've described until now is results that date back to at least 4 or 5 years. So it's kind of the backdrop of what I want to talk about in my next lecture, which is to explain how this framework can be extended to the setting of orthogonal groups of more general signatures. And that would lead to a theory that has a broader applicability to all, to various settings where generating class fields of non-CM fields, not necessarily real quadratic fields. And so that's what I'll do in tomorrow's lecture. I'll talk about these rigid meromorphic cocycles for orthogonal groups. And in the meantime, I just want to thank you all for your attention to this first lecture.
Actually, now that it's time, the 11 a.m. in Seoul, but 10 in the evening in Montreal, Canada. So I extremely thank you, the Professor Darmon. So now
it was my pleasure to come at least virtually to Korea.
And then everybody, don't forget that tomorrow morning, 10 in the morning in Seoul, 9 in the evening in Montreal, Canada. So there is another excellent lecture is waiting. So, Professor Darmon, good night.
Good night. Thank you.
Yeah. Thank you very much.
Thank you so much.
Yeah.